thank you so much. I'm going to get going. All right, so first, thank you so much for having me here today. I really appreciate it. I'm a big fan of master gardeners. I have worked quite a bit with master gardeners. I'm not a master gardener myself. It is on my to-do list, though, to get there eventually when I have a little bit more time. As Judy mentioned, my name is Kirsten Kurtz, and I am a soil scientist at Cornell University. As part of that role, I kind of wear many different hats, one of which is I manage the Cornell Soil Health Lab, which is the leading lab of its kind in the world. I'm also a graduate student at Cornell working on my MS in natural resources. I'm on track to finish that this year, I'm pleased to say. And I'm also an artist. My undergrad is actually in fine art. Although I was raised on a 200-acre organic farm and I've worked in ag my whole life, I really kind of formally wanted to be an artist when I was younger. Eventually, I kind of left that to pursue my interest in science and in agriculture. But once I came to the lab, I started to get interested in art again, and I developed this technique of painting with soil. And I'm not going to talk too much about that today, but I just wanted to mention that that's something else that I do and include 2 of my soil paintings here on the screen. I've also included some contact information, including my email, my Instagram, which is mostly about my soil painting work, but a little bit about soil communication and about soil health, as well as the link for our website at the Cornell Soil Health Lab. All right, so I want to start by talking about why I love soil and why I've dedicated my life to studying soil. The most important thing, I think, is that 95% of our world's food comes from soil. I'm often asked if we could replace this with hydroponics or greenhouse systems. The short answer is no. If you think about how most of us subside on grains and other things that are derived from grains, think of dairy, things like that, it's really easy to understand that we aren't going to be able to replace soil. At this point, we've lost 1/3 of the world's soils to degradation of various kinds. And along with that, we've lost 50 to 70% of soil carbon stock. So I'm sure you guys have heard a lot about carbon and soil. This is a big deal these days, and I will touch on that today in my talk. What's really important to understand is that soil is a huge carbon sink, and it actually stores more carbon than the atmosphere and plant life combined. So that is where the majority of the carbon is on our planet. All right, and I kind of wanted to start off today with a little crash course in soil science. I know that this audience is probably more well educated about what soil actually is than the average audience, but I want to touch on some kind of core concepts in order to better explain sort of what we do in the lab. So one of the things that's really interesting about soil is it's about 50% solid, right? So of that solid, that's rocks and minerals. Those rocks and minerals are typically derived from what we call parent material, which could be stone and other things that are worn down and become sort of that basis for soil. And then that full other 50% of soil is made up of water and of air and other gases. And that water and air moves around sort of the solid part of the soil. So you can look, I think, at this picture I have here on the screen of this macro aggregates. So think about those sort of round little chunks as being that solid percentage. And then that water and air and gases are moving around those what we call aggregates. And that's where a lot of the life of the soil lives. That's where a lot of the activity is happening. And then, of course, soil has organic matter, which is one of the key parts to making it a living system and to making it function for us as farmers or as gardeners. 5% is kind of an ideal organic matter amount. Pretty much you want more, as much as you can get in general. But like ag lands might have down to 3.5% organic matter, things like that. You guys in a gardening setting might have much higher organic matter levels than that, depending on your soil texture. Okay, so one of the important things, the other important things to understand is that that organic matter is not all the same, right? So organic matter is made up of different kind of levels of decomposition, and we call that the living, the dead, and the very dead. So the living would be like plant residue, microbial biomass, really like compost that's kind of breaking down. The dead is this active organic matter that's a lot more stable and that is generally a food source for the microorganisms. And then the very dead would be extremely stable organic matter that kind of isn't really going anywhere. The main functions of this organic matter are nutrient storage and that it improves soil structure and protects that soil from erosion. And I think that you're all probably pretty familiar with what a soil profile looks like, but if not, this picture at the bottom of the screen here is a soil profile, and that's kind of looking, if you dig in under the surface, that's what you're going to see. And you can see that organic matter is very dark, and it typically is building up at that surface level. And that's really what we're gardening in. Okay, so soil is alive, as I've mentioned. There are more organisms in a teaspoon of soil than there are people on the planet. This is often said, it's incredibly true, but only for a healthy system. And that life of the soil is primarily made up of microbes, bacteria, and fungi living together, along with larger organisms like your earthworms or even owls that burrow underground. All of those types of things are part of what we call the soil food web. And these soil microbial community primarily is there to help decompose soil organic matter, to again increase nutrient availability and storage, to protect plants against pathogens. So we know that a healthy soil is going to grow a stronger plant that is more likely to be stronger than a pathogen that would be in the soil attacking it, for instance. And then this life in the soil also greatly increases our aggregation and pore space. By far, one of the most, if not the most important soil property is soil texture. I understand that you guys have very sandy soil there, and I'm going to talk a little bit about managing sandy soil, and I'm happy to take questions about this at the end. It certainly will give you benefits and also complications to have a sandy soil. But when we're talking about soil texture from a laboratory standpoint and from a gardener's standpoint, really, we're talking about the percentage of sand, silt, and clay that's in that soil. And we measure this using the textural triangle, and you basically just look at it at what your percentage is. And let's say you have 50% silt and 30% clay and 20% sand, that's going to be a clay loam, for instance. And what's really important about these soil textures is that it influences many important processes for your soil, including water infiltration, water holding capacity, nutrient holding capacity, aeration. And I think, as you can see on this graph I've included on the slide here, that for sand, for instance, you're going to have really great water infiltration. That makes sense. It moves right through the system. Really great aeration, which means that your air also and your gases can move easily through the system. But you're going to have a low water holding capacity, and you're going to have a low nutrient holding capacity. It's just kind of how it goes. But as I mentioned, there's ways to manage for this, which I will talk about towards the end of my talk. All right, so I wanted to briefly touch on pH. I think that you're probably all quite familiar with pH. One of the most important things about pH from where I stand as a soil scientist is about the nutrient availability. I hope that many of you have seen these types of charts before, but this gives you an idea about why we try to keep our pH within a certain range. Typically, most soils, you really want to keep it for the average garden or the average field crop between 6.5 and 7, something like that. And it's because that's going to give you the most available nutrients. As your pH goes lower or higher, it's harder for those nutrients to be available, for them to be pulled up by the plants. I also want to make a kind of a plug here for growing what will grow well where you live, right? So like if you happen to have low pH, maybe you should start a blueberry farm. It's really hard to change pH. You have to do it every year. You can see at the top, I included some short and long-term methods for lowering and raising pH. Again, I'm assuming you're pretty familiar with these ideas, but I want to encourage folks to think about not changing the soil so much, but growing a crop that will thrive in that soil, because overall you're going to have a more successful system generally. All right, so with that was kind of like background, some like key points on soil in general. And from there, I want to move into soil health. So soil health is defined by the NRCS as the continued capacity of soil to function as a vital living ecosystem, living being the key word here, that sustains plants, animals, and humans. This is a relatively new definition of soil health. I think it's a very good definition of soil health. And really, from our lab standpoint and from most scientists' standpoint, I think when we talk about soil health, we're looking at the biological, the physical, and the chemical aspects of soil together. And when we're thinking about the biological, I'm really talking about the biota, so that life of the soil. I'm talking about the carbon, and I'm talking about organic matter. And those are all very intertwined. But that's typically what we're talking about when you hear someone say the biological parts of soil, that's what they mean. When we're talking about the physical aspects of soil health, we're talking about structure and texture. So I touched on texture. Structure is going to be, you know, like your depth, your available water capacity, things along those lines, your compaction, those types of issues, the actual physical state of the soil. And then the chemical is going to be basically what you are all probably used to receiving from a soil test. So that's going to be your major and minor nutrients and your pH. And then typically they would also give you your organic matter percentage. And then along those same lines, we can talk about what those healthy characteristics are and separate them again into these different, the biological, the physical, and the chemical sections. So with the biological, we're talking about tilth. So that's kind of how fluffy your soil is. We're talking about having a low pathogen and pest pressure. We're talking about having high beneficial organisms. So that's the good life of the soil that we want to have there. And we're talking about low weed pressure. When we're thinking about the physical healthy soil characteristics, we're really looking for depth of good soil. We're looking at water storage and drainage, and we're looking at a resistance to degradation. So how stable is your soil really? And then on the chemical aspect, we're really looking for sufficient nutrients. So like we don't want more phosphorus or nitrogen, especially than you need in a year, because that's going to run into our waterways and cause all sorts of other issues. So we're looking for like that kind of perfect amount of nutrients. And we're also interested in that being free of chemicals and toxins, like heavy metals and things along those lines. And then following this same kind of thought exercise, we can see the constraints and what they're typically associated with, right? So we're talking on the biological, a low water retention, high pathogen and pest pressure, low beneficial organisms, weed pressure. I mean, this is things I think we all have lots of experience with. You know, on the physical, we're talking about compaction. So we're talking about surface or subsurface compaction under the surface of the soil, poor aggregation. Both of these things I'm going to talk about in a lot more detail coming up here. And then on the chemical, that low nutrient retention, salinity and sodicity. So this is salts that can build up. So I'm not sure if any of you guys are working in greenhouses or hoop houses or things like that, or with irrigation. But if you are, salts can really build up in your soil, which we call salinity or sodicity. And that's something that you want to measure and be aware of, because that can start to really hurt your growth potential over time. And also, as I mentioned before, the heavy metal contamination. All right. So with that, I kind of would like to introduce our lab. We're the Cornell Soil Health Laboratory, and we developed a test called the Comprehensive Assessment of Soil Health, or CASH. I actually came up with that name thinking like, oh, it'll save you cash. You know, that was kind of my idea. And in general, just because I have this art background, this is a total side note, I think it's really important to have acronyms that actually like mean something and sound like something to help people remember what you're talking about. Anyway, so we're kind of interchangeably called, you know, the CASH test or the Cornell Soil Health Lab. I just kind of wanted to lay out that both of those are us. So we opened in 2007 as the first commercially available soil health test in the world. We've tested well over 10,000 samples from around the United States. Mostly, I would say probably 90% are from the United States, and then we also get them from around the world. We do hold the largest global soil health database, which is really important because how we interpret your results is really against everything else we've gotten in the lab. So the more data we have, the better job we can do of telling you kind of where you fall. We all have additional responsibilities in research, outreach, education. So we have a pretty extensive book we call our manual. We have fact sheets, and they're all available on our website, as well as tons of information. We have videos on how to take samples. Everything's available for free. We really believe in our extension responsibilities. Cornell is also a land-grant university, so we have responsibilities to the people of New York, and I really consider that I have responsibilities to the whole country in a lot of ways. And what we do in our lab is that we quantify soil health, right? So we're putting numbers on it, you know, and really it's kind of like what I said, it's about saying where you fall in comparison to that of your peers. We're working right now on doing regional. We're getting really close to having New York pretty dialed in. Eventually, you know, there will be the East Coast will have its own section, possibly even states will have their own places. And then you can see where you fall against everyone else in Cape Cod, for instance. And when we were deciding what all to look at, I think originally they were looking at 64 different soil health measurements. And we distilled it down to much less than that. And we're looking for things that are sensitive to management, easily like replicable, as in we always get the same results every time we test it, or are very close to the same results, and things that are relatively inexpensive to do. So we have a lot of biological tests, especially because carbon is turning into such a big deal. So on the biological aspect, we measure and quantify organic matter, soil protein, soil respiration, active carbon, and total carbon, total nitrogen. On the physical aspects of soil health, we quantify texture, aggregate stability, and surface and subsurface hardness. And then on the chemical aspects, again, kind of what you would expect from a typical soil test, we quantify pH, major and minor nutrients. And then we put all of this information together in a holistic way. And that's what's really important. We don't consider any one piece of this information more important than anything else. It all comes together. It all goes into your overall soil health score. And because all of these things are important, you know, we really kind of before I even became a soil scientist. So I've been working with the lab now for almost 10 years. I'm about to hit my 10-year anniversary. And in the beginning, people really weren't kind of buying this, but it's really come a far way as far as like everyone understanding that if you only know the chemical, you're not going to really understand what's going on with your soil. So I want to show you guys what our report looks like. This is the first page of a multi-page soil health report. And I'd like to point out that we have these separated by physical, biological, and chemical aspects, which I hope you can see all the way on the left-hand side of the report. And these two soil samples were taken about 10 feet away from each other. All right, and the one on the left, that was taken from a plant breeder field on campus, at the Cornell campus, that's been tilled multiple times a year and cultivated multiple times a year. So they're pulling multiple harvests off of this field a year. And then the one on the right-hand side of the screen is the grass directly next to the field, which isn't even that amazing. I mean, that's where we drive the tractors, you know what I mean? But still, if you look at the difference between these fields, you can see major differences. And I'd like to draw your attention to the chemical aspects all the way at the bottom, because you see that actually in both cases, the chemical aspects came out looking pretty good, and they really did. But when we look at the physical and the biological aspects of the report on the left, we see that there's major constraints indicated by the color coding system. So dark green means everything is going really well. Light green, you're doing well. You have a little room for improvement, say. Orange, you're kind of average. Yellow and red, that's where you start to have some serious problems. So for the case of this, we actually will highlight the constraints that you can see on the left-hand side, and we'll say, all right, your aggregate stability, 13.4, that's a percentage. That's very, very low for aggregate stability, and that's going to cause all of these types of issues with aeration, infiltration, etc. And this here is an example of comparison sampling. All right, so comparison sampling is really important. From where I stand, I really believe in comparison sampling. And I'll draw your attention to this little map that we see here on the screen. And we're looking at two different sections. We're looking at a no-till, so this is something that, this is conventional ag, but this is an area that's been managed without tillage. And then in zone Y at the bottom there, we see plow till, and this is an area that's being managed with tillage. So in this case, we're interested in what the difference is between the no-till and the plow till as far as these soil properties. So what you would want to do is you would want to go out and sort of sample in a W or an M pattern across your area of interest. And you would take a subsample at each location. And then at the end of that, you would mix all of those samples really well, and you would pull out 4 or 5 cups, depending on what package you get from us, to send to our lab of fresh soil. And that's what we test. You notice in this picture, there's a low spot that's being avoided. You want to definitely go out and take something that's representational of your field. So you're going to say, so you're growing corn, you're going to want to get the average height of corn. You would sample there, not the corn that's doing super well or the corn that's doing super crappy, right? So you're thinking about it being a representation. Another method would be to sample your garden and then sample your yard right outside of that. And that's a way to directly see how your management is affecting your soil. It really teaches you so much more than you can possibly learn with one sample. And I don't say this to try to drum up business. We're incredibly busy. It has nothing to do with that. It's just that you, as a client, will understand so much more if you do it this way. All right. So now I'm going to get into the lab, and I'm not going to talk too much about how we measure every single one of these things within the lab. I'm happy to answer any questions about that, of course. We do have our SOP, which is our standard operating procedures, posted online for anyone to read. But I'm going to kind of more talk about what information we're trying to get at and what that really means. So again, here's the list of our biological indicators, that life of the soil. And I just want to point out my favorite soil organism in the bottom left corner. That's the tardigrade. That little creature can survive in space. It can be frozen for thousands, maybe even millions of years and come back and be totally fine. There's amazing, amazing creatures. And just one example of this highly diverse, very unknown life that we have under our feet. All right, so of course I have to start with soil organic matter. So soil organic matter, it's built up by things dying, and breaking down in the soil, right? Grasses do a really good job of building up soil organic matter. You can see in this picture here on the screen, the grass roots going very deep down into that soil profile. That very dark color, that's indicative of a very high organic matter. And those roots, of course, eventually die, and then they're bringing down this organic matter deep into the system for all of these different microorganisms and that life of the soil to eat, which keeps on improving the system. So it's really quite simply a measure of carbon-containing material that's derived from living organisms, including plants and other soil-dwelling organisms. That is where organic matter comes from. And of course, also it would come from you putting wood chips or compost or things like that on your garden. That would be breaking down, and that would be creating and building up your soil organic matter. And as I mentioned earlier, all soil organic matter is not the same. So I've included kind of in the middle of this slide, this little pie chart that shows that total organic matter, which is measured by loss on ignition, which means you burn everything off. And that's the slide previous to this that was showing all of this, right? This is that total organic matter. And of some of that organic matter is what we call active. And that active organic matter is very important because it serves as an easily available food source for the microorganisms. And one of those is soil protein. Now, this is a test that we developed at Cornell ourselves probably about 5 years ago, maybe a little longer than that. And soil protein is derived from plant residues in the soil, so that's typically where it's coming from. And the best way to think about what soil protein is for me is that it's nitrogen. We all know what nitrogen is, right? So it's organically bound nitrogen. It's nitrogen that's in the soil organic matter that can easily be metabolized and uptaken by the microbial community, right? And then they kind of break it down and make it available for plant uptake. So it's basically a way to measure nitrogen, which nitrogen is very hard to measure because it comes in a bunch of different forms, including gases and things like that. So this is just one more way for us to get at quantifying how much nitrogen is in your soil in that soil organic matter. So this is a very important test. We also measure soil respiration. So all of those microorganisms in the soil are basically respiring CO2, right? So carbon is a system, much like nitrogen is. And as the carbon is coming into the system, some of that is being released by the microorganisms in the form of CO2, while hopefully most of it is being sequestered in the soil. And from this release of CO2, we're able to get at the metabolic activity of the soil microbial community. So what this means is that we don't measure your respiration and say, you have 1 million soil organisms in this sample, and that falls in about average and blah, blah, blah. It doesn't really work like that. What it is more is it's about how well are they functioning? Because you could have a lot of soil organisms that are kind of like sleeping and not really doing anything for your system, or you can have soil organisms that are like working hard, breaking down that organic matter, releasing that CO2, and that tells us a lot more about how that soil is functioning. And we measure this quite simply in our lab, basically by trapping and kind of waking up soil by adding a little bit of water. And then we trap that into a little jar and we measure the CO2 that's released. We also measure active carbon in our lab. This test has been around for a really long time. It was developed by Ray Weil, who's one of the world's most famous soil scientists. And this is an indicator of the part of that soil organic matter, again, that can be available for easy uptake by that soil microbial community. But instead of being nitrogen, in this case, it's carbon, right? So this is just another way to get at that. And this is definitely one of the best overall indicators of the soil health in general. We also look at total carbon, total nitrogen. So total carbon is quite simply looking at all of that carbon. So if you're looking at organic matter, that's not going to get at carbonates or other types of, or biochar, things like that, very, very stable carbon. It's not going to measure those, so it's important to know that total. And then the total nitrogen is a way for us to get at measuring nitrogen in all of its various forms, including in its gas forms, as I have included here on the screen. All right, so we also have a suite of physical indicators, which I am going to go through, and I like to always start with wet aggregate stability. So aggregates are basically those crumbs of soil, and you can see all the way on the right-hand side of your screen a soil sample that has very well-formed aggregates. And this, as you can imagine with one of those first slides I showed you, leaves a lot more room for that life of the soil to live around it. And these pictures that I have here on the screen are actually from my research, which is in Nebraska. And the one all the way on the right is from a remnant prairie. So this is a prairie that's never been tilled or cultivated by modern agriculture. And then in the middle is directly adjacent to that remnant prairie active ag land with corn soy rotations. And this is basically what soil looks like if it's been used really hard with no consideration of soil health. And you can imagine that middle soil does not function nearly as well as that native soil does. And when it rains, this soil in the middle will basically fall apart, go into our waterways, flood because there's no spaces for it to drain, whereas the other soil, that remnant prairie, can really hold up to basically anything you send at it. As I mentioned earlier, we also measure and report on soil texture. I just wanted to include these pictures that kind of show you how different it can be with the clay versus the sand. And of course, you're always hopefully have something in between these for farming, but you know, there's ways to work with it no matter what you have. Okay, so we also look at available water capacity. Available water capacity is quite simply how much water your soil can store. We look at it at two different points. The upper end is called field capacity. So field capacity is where your soil is completely saturated, like after a major rain, but it's not free flowing underground due to gravity. So it's as much as can possibly be held by that soil. The far other end is permanent wilting point, which is where your soil is so incredibly dry, it actually sucks the water out of the plants themselves to the point that they die and they can't come back from it, right? So these are the two extremes. They're very different depending on what type of soil you have. Unfortunately, a sand has quite a small available water capacity compared to a silty clay loam or something like that. Just part of the game, but it's always good to know more information, at least where I stand. All right, so we also look at surface and subsurface hardness. And what we use to do this is we use this tool called a penetrometer. This is the only test that we do that's actually done by you or our client themselves and not by us. And then you would send us the data and we would interpret it and add it to your report. So basically a penetrometer, you can see these two gentlemen are using it here on the screen. It's a rod that you push into the soil and it records resistance, in pounds per square inch. So what we're looking for is what the highest level is between 0 to 6 inches, and then from 6 inches to 12 inches. So you're pushing down and you record on a sheet of paper, it's on the back of our submission form, the highest number that you see. And basically what we're hoping to see is under 300. So 300 PSI, we know that that's root limiting, and it's very hard for roots to push through that level of compaction. So folks who send lab samples to our lab, we actually mail these out for free and let people borrow them for a couple weeks, and then they just ship them back to us. Also, typically you can borrow these from your NRCS field agents. Cooperative Extension often has things like this, and you can go out and measure your compaction in the field. It's super important. It can really help you to find plow pans, compaction layers, things like that, that can really be a major issue for your farm. All right, and then we also look at the chemical indicators, pH, major nutrients, nitrogen, phosphorus, potassium, those minor nutrients, that's like magnesium, calcium, things like that, and report those back to you. I'm going to spend no time on this because this is something I assume that you're relatively familiar with. All right, and then I guess I threw one more slide in here from my research. I can't quite help it as I'm working very hard to try to finish that right now. And this is looking at the organic matter in paired plots. So these are box plots. The way to look at this is that these are paired. So the first two samples, 1 ag, 1 P, those go together, 2 ag, 2 P, 3 ag, 3 P, and then the last 4 ag has 2 samples that go with it, 4 PA and 4 PB. And this is my paired samples of that agriculture next to the grasslands. These were all taken basically adjacent to each other, same slope, same soil type, all of these things. And I just wanted to show to you how much organic matter you can basically lose by not farming your fields properly. And especially in the case of Nebraska, it's like some of the best soil in the world. So I'll point out like the most extreme example, which is 3 ag and 3 P in the middle. And here we see that that agricultural soil had about 4% organic matter, which really isn't terrible at all. But then what was there was more like 6 to 7% organic matter. So it's really just phenomenally important that you manage your organic matter in your soil properly. All right, I know this is so much information, but I promise I will answer any questions you guys have. I hope you're all with me, because now I'm going to move into managing for soil health. This is a picture from Longwood Gardens. I hope that some of you guys, maybe all of you guys, have been there. It's in Philly, kind of below Philly. It used to be like a DuPont estate. It's really amazing. Highly recommend. I'm a big fan of botanic gardens. And I've actually worked a little bit with these guys and a bunch of botanic gardens who understand that soil health is really important. And I only included this picture because it's so pretty. All right, so a few years ago, probably like 5 years ago or something like that at this point, I was working with some dairy farmers in Western New York. And as I was preparing for my talk, I came across this concept of feeding your underground herd, right? So if we think about there being more organisms in a teaspoon of soil than people on the planet, and I've talked a little bit about what they need to eat, right? This organic matter of these different types of organic matter to break down to then give to our plants. it's really obvious that we need to feed that herd, right? So you're kind of farming your soil. And I was able to distill it down into 6 key concepts. All right, this is like basically all you need to know about improving your soil health. You need to increase your organic matter. I'm going to talk on the next slide about how we can do some of these things. You really want to have cover. You want to use cover crops if possible. You want to plant cover. There's a lot of different ways that you can do this. It doesn't have to be cover crops. I understand you guys aren't corn farmers here. You know, again, I'll talk about this a little bit later. You want to increase your rotational diversity, right? So we know that there's certain organisms that like to live with certain plants. So the more plant species you have, the more microbial diversity you will most likely have. And diversity makes for a more resilient system, much like how it does in life. It also does in soil. The more diversity you have, the more likely that system is going to have to be stronger than a pathogen that's thrown at it, for instance. You want to control your traffic. So you want to drive on your field, walk on your garden, what have you, as little as possible. And you definitely don't want to do it on wet soil. All right, so wet soil compacts super, super easily. And I understand sometimes you have to get out there and you have to till, but it really, you probably will be paying for it for many years, if not generations. It's very, very hard on soil to drive on it when it's wet. And in general, you want to reduce tillage. So, you know, of course, I'm thinking of tillage on a farm, but I also mean rototilling, right? So when I had my own little organic farm, I got into it a lot with my partner about like tilling, and it's true, you can still build up really good soil and till all the time, like especially an organic vegetable system. But like the less that you till, it'll just build up better. You know, like don't get me wrong, I've seen many systems where they till all the time and it still has amazing soil, but I still wonder how much better it could be if they could cut that back a little bit. Okay, so then I was thinking about, you know, talking to you guys. I know that you're master gardeners. So I wanted to tailor this idea of feeding the herd a little bit more towards this audience. I have a picture here of a beautiful permaculture garden I found somewhere. Anyway, so when you're thinking about building up organic matter, you're going to want to think about compost and mulch, right? So mulch, especially what I know about your all's area with a lot of sand, I really recommend mulch. It's a way to have that cover and to have organic matter that breaks down slowly. Compost is going to break down more quickly. It's nice to have different types of organic matter so that you have it breaking down at different levels. It'll help your system overall a lot more. So this cover crops idea, this don't farm naked, soil really doesn't like to be exposed like at all. You know, so ideally you don't ever have bare soil like that kind of romantic image that we all have of like the big fields and it's just soil with like maybe the, you know, kind of like the hills throughout it, right? Like that's actually the most vulnerable that soil will ever be. If it is windy, if it's raining, if it's not healthy, it will blow away, it will wash away. It's a really bad system. So luckily in your case, you can use perennials. You know, you can also do mulching. You can do these kinds of things that will really keep that cover. It's really, really important. Again, diversity, you know, you're going to want to think about rotating your annuals. You should be rotating them ideally throughout your farm, throughout your gardens. And again, that diverse species selection, you know, try as many different types of species as you possibly can. You want to think about your traffic. You want to think about tilling when the conditions are correct, right? So really, when you want to till is when you like reach into the soil and it kind of just like breaks apart. It's not too dry. It's not too wet. It's this, I'm sure you guys are all probably very familiar with what it feels like, that sort of nice tilth. That's when you want to be tilling. You really don't want to be doing it while it's wet. And if you at all can, you should be driving in the exact same tracks. So like always following the same places while you're working your garden or your field. And again, just keeping those disturbances to a minimum. All right, so then I just wanted to kind of bring it back to the report here for a second. And I briefly mentioned this, but this is actually the first of about 12 pages. So for each one of these indicators, we'll talk about like what surface hardness is and what your result means regarding surface hardness, right? And then on the last 2 pages, we have short and long-term management suggestions. So I kind of blew up one of these so you guys don't have to try to read this really small writing. And in this case of this report, the person's soil protein was low. So they had kind of a low result. And then we'll say short term, you know, you can add nitrogen rich organic matter, you can incorporate a young cover crop biomass, you can plant legumes, which will fix that nitrogen and other things. Long term, we're going to say reducing that tillage, monitor and maintain your pH, monitor and maintain your carbon and nitrogen ratio. And this is kind of where we get at how you can address issues in your field. So because we work with so many different types of growers and farmers, we don't want to say you need to do this or that because we don't know. That might not work for you at all. But the idea here is that one of these concepts or a few of these concepts will work for your system. So I really recommend taking advantage of that. All right, and then thank you. I really appreciate it. I know I just went over a lot of information. I just wanted to share that if you are interested in my soil painting work, I do talks on that also quite regularly. I have a website, soilpainting.com, where you can check it out. There's a couple documentaries have been made about what I do, including this Art of Soil one that you can find on YouTube. And again, my contact info, shameless plug for my Instagram. And with that, I'm ready to take questions. Thank you so much.